Good afternoon, everyone. Greetings. Thanks for being here. My name is Stefano. I am a postdoc researcher at the Politecnico di Milano, which is Italy's largest technical university. We have like 42,000 students. And I'm also the CTO of a small consultancy called Secure Network, based in Milano, Italy. The argument of my talk today is anomaly detection, and for those of you who maybe already know me, this is not surprising, but what I will present today is anomaly detection through a particular type of system call argument analysis. And my outline is I will begin by building a case for anomaly detection systems. Why do we need them? Bear with me if you already heard me ranting here on Focus IDS mailing lists on this topic, because I use this part of the presentation to draw forth some requirements that are the ones that I try to fulfill with my research. Then I will present to you the state-of-the-art algorithms for detecting intrusions through anomaly detection on in host-based IDSs. In particular, the ones dealing with system calls. And we will see that there are a lot of systems analyzing sequences of system calls, and a few systems, a couple, analyzing arguments. And I will show you how we combined both of these directions along with some other tricks in order to try to create an algorithm which can detect intrusions in an unsupervised manner. The defender's problem is one of the oldest in the art of war. The problem can be stated as the fact that the defender needs to plan for everything. So when you defend a system, you need to check every single part of it for possible vulnerabilities, while the attacker needs to find just one attack point. That's why I became a penetration tester instead of being a security administrator. It's far easier to become a penetration tester. Being overconfident is the common mistake of defenders. And there are a lot of examples. One example I particularly like is the battle between King Darius of Persia against Alexander Magnus in Gaugamela Plains, 331 before Christ. Darius had already been beaten by Alexander in a couple of narrow valleys. So he thought that he should choose better the next terrain for the next ground for their encounter. He spent 6 months raising every single hill and rock of Gaugamela Plains to the ground. So basically, after 6 months of works, Gaugamela Plains was exactly like a billiard pool, totally plain. And in these plains, he fought against Alexander with an army which outnumbered Alexander by 5 to 1. And being outnumbered 5 to 1 in a huge desert plain means being dead, basically. What happened is history. Alexander charged straight to the middle of the Persian army, of the huge Persian army. And basically what Darius understood was that Alexander had accepted to die, but he wanted to kill him before dying. So he was charging in direction of his throne. And what Darius did was what every common man would have done. He fled. And when Darius fled, the Persian army dissolved. And, well, if you wonder about the sword of Darius, 3 months later, it was found, well, his head was found over the top of a pool. It was probably killed by one of his own lieutenants. Anyway, just not to end up like Darius, the key is acting sensibly. We cannot amass an army of firewalls, intrusion prevention systems, whatevers, which is large enough to protect us against all enemies. And acting sensibly is really the key, and I suggest you, I point you out to Beyond Fear by Bruce Schneier, which is a must read, in my opinion, for anyone who works in security. I like to quote the Murphy's Law on complex systems, which states that the only difference among a system that can fail and the system that cannot possibly fail is that when the system that cannot possibly fail fails, it fails in an unforeseen manner which is totally devastating and impossible to repair. Many security systems are just like this. Many security systems have concentrated every effort on defense, every effort usually on perimeter security. Sometimes some effort goes into building secure systems inside the perimeter. But often we forget to take into account that at some point in time, our system will, not can, will be broken into by someone who is smarter than us or simply has more time to try to attack our systems than the time we have to spend trying to defend it. So, the mantra of the security experts should be plan for the worst and pray it doesn't get even worse than that. And to do this, we have to design systems that can, of course, withstand attacks and fail slowly, fail gracefully. We cannot have brittle systems that once that one of their components is compromised, fail totally. We must design systems that are capable of recovery, so systems that can be restored to their previous state without too much effort. But we must also think of designing systems that are tamper evident, which means systems where intrusions can be detected. And computer systems per se are not tamper evident. They are the less tamper evident thing of the world. So we need things, we need systems that alert us whenever our systems are broken into. An intrusion detection system is just like that. It's a system, not a software. IDS software is one of the components of an intrusion detection system. But an IDS is a system that tries to find out if an information system on the whole has been compromised. As such, an intrusion detection system is a complex part of your networks or your computer security infrastructure. The so-called IDS software, they are just a component of a good intrusion detection system. Because an intrusion detection system usually closes its loop on a human being. What I mean is that a skilled human, such as most of the people attending this conference, looking at logs in a system, is an intrusion detection system. A skilled network administrator, again, as many of you, looking at TCP dump is an intrusion detection system. How many times did you detect something anomalous on your network simply because you fired up TCP dump and you spotted a single packet in a flow which was not supposed to be there? Other forms of intrusion detection systems apply. A company maintaining and monitoring a firewall is an intrusion detection system of sort. The one thing which is not an intrusion detection system is a software you bought, you placed it on a PC, or you bought directly an appliance, you plugged it into your network, and you put it on a shelf. That's not an intrusion detection system. If no one is getting information out of that box, that's not an intrusion detection system. An intrusion detection system is a component of a more complex security infrastructure, and it's the last component of a security infrastructure, actually. So when you have done everything else, you will begin to do IDS. If you have not done your firewalls, if you have not done your basics, then IDSs are useless. And an IDS is not designed to substitute a firewall or to be compared to a firewall. Some years ago, a couple of years ago, Gartner produced a report where they said money slated on intrusion detection should be better spent on firewalls. Yeah. That means a couple of things. First thing, money slated on Gartner reports will be better spent on firewalls. And the second thing is, if you think that an intrusion detection system, whether or not you dub it again into intrusion prevention system, is going to help you prevent attackers getting into your network, you are up for a huge surprise. Because intrusion detection systems have been designed since their first inception to alert you of a compromise which has already been done. So, detection should come together with reaction. Reaction is needed to make intrusion detection systems efficient. So, this brings me up to a point. The intrusion detection system must give out actionable results. So you must you need to have a system which gives you the information you need to counter an attack. If your system does not give you this information, then it's not a good intrusion detection system. Another thing that I'd like to point out is that reaction without human supervision is a dream. The network defend thyself spots by Cisco and others, well, they are dreams. So if you want to buy dreams, by all means, go ahead. But in general, when I speak of reaction, I don't mean an intrusion detection system automatically doing something. I mean an intrusion detection system giving a network administrator the tools in it for getting his job done. So, in order to introduce you to my research, and knowing that many of you maybe already know this, I will briefly do a taxonomy of intrusion detection systems in two: anomaly detection and misuse detection. Misuse detection are the intrusion detection systems you probably work with. If you have an intrusion detection system on your network, whatever the price tag, whatever the brand, it's basically a misuse-based system. What does a misuse-based system do? It flags attacks by using descriptions of the attacks. So it tries to directly recognize attack activities. This is cool. It works very well. It's easy to implement. It's easy to sell. Gives actionable outputs. You obtain all the knowledge you need. You know that this type of vulnerability has been tried on this type of server, and guess what? This type of server now sends out recognition packets to other servers in your network. So you know everything you need in order to react. Unplug the server, do forensics, reinstall the machine. The problem is this type of systems does not work very well. We all know that. I think there's very few people in the information security arena that would tell you that intrusion detection systems currently work very well. This is because of two problems. One problem is that people consistently try to have intrusion detection system do something else than what they're designed to do. And second part is people selling intrusion detection system have sold them as being able to do things they are not able to do. There's a lot of misuse detection vendors that will swear on a Bible that their intrusion detection system can detect 0-day attacks. 0-day attack is an attack on an undisclosed vulnerability in the common parlance of people in information security. A misuse detection system needs a description of an attack in order to catch that attack. So if you have the description, that attack is not a zero-day. So where's the trick? The trick is that they redefined what they call zero-day attack. They call zero-day attack an unknown exploit against a known vulnerability. So they detect attacks against that vulnerability, and they are able to detect also new exploits for that same vulnerability, which is, yeah, it's good. It's something they were supposed to do from the beginning, but it's not zero-day attack recognition. The only way to recognize efficiently attacks that have not been described before is to have an anomaly detector, a system that can flag anomalous behavior without describing attacks. A system that flags anomalous behavior by using, for example, statistical means, learning algorithms, whatever you want. Why is this type of algorithms capable of detecting zero-day attacks? Because it doesn't need as an input the description of attacks. But on the other end, so if these anomaly detectors are so much more powerful than misuse detectors, why aren't we using them? Why is there just a couple of vendors of somehow anomaly-based detectors on the market? Well, because building good anomaly detectors turns out to be difficult. So we have a simple solution to the intrusion detection problem, being misuse detection, which does not solve the problem. On the other hand, we have a complete solution of the problem, anomaly detection, which is difficult to do. So if misuse detection is a bad idea, and it's a bad idea for a number of reasons, the first and foremost being the one I already stated, it cannot recognize zero-day attacks. It cannot recognize unknown vulnerabilities being exploited. It cannot recognize vulnerabilities being found on your custom application. If you have a custom web application, and almost every shop in the world nowadays has one, or more than one, and it's critical, you will want that application to be protected. But your average misuse detector cannot detect attacks against a custom application. Yeah, it can detect some forms of attacks based on generic signatures. But since generic signatures usually are the ones most prone to false positives, to generate huge tons of false positives, first thing you will do when you receive an intrusion detection system will be to turn off the generic signatures because they generate false positives. Also, attacks are polymorph. If I write a signature for a web-based attack, for example, and the web-based attack can be exploited through the use of UTF-8 encoded characters, you have as much as 9 different encodings for each character in the string. So I have a choice. Either I canonicalize the strings, so every time my intrusion detection system detects this is an URL, so canonicalize it, see what it means in standard language, and try to apply the pattern recognition on the canonicalized string. Or you have to generate a huge amount of different signatures, which is evidently unfeasible. But there's a lot of other ways of making attacks different. Think of admutate. Admutate is a very well-known concept. Admutate picks up the payload of your average buffer overflow attack, encrypts it, prepends a decryptor to the payload, and then executes the decryptor, and the decryptor decrypts the payload and executes the payload. That's a very clever idea. K2, Canadian hacker, created this idea some years ago, 1998, I think. This idea, if you ask to any anomaly, any misuse-based detector vendor, if they are able to detect admutate, they are Why? Because they detect the decryption procedure, the part of shellcode which decrypts the rest of shellcode. But it's obvious to me and to you and to everyone that I could write a different program, a different set of opcodes, which does something very similar to admutate, but as long as it's not the same routine, all these signatures will be useless again. So, and so on and so on. We have generic signatures that match long sequences of knobs, 0x90, in whatever packets you are seeing through your network, because a long sequence of knobs usually is a sled for a buffer overflow. A clever attacker will substitute that with a jump to next, JMP 0x00, and will obtain the same result with a different instruction. And it will have a lot of different ways to combine these things. Whatever pattern you put into your signatures, it will find a way to go around it. I will also point out that besides specific ways to polymorph an attack, many misuse detection systems still nowadays are vulnerable to the attacks described in the great work by Thomas Ptacek and Tim Newsham, 1998 still. It's 2006. 8 years have passed. If you pick up and fragment some packets and then try to send them with wrong alignment and some tricks at network level, most of times you can successfully find a way to evade your ISS, snort, or whatever probe. So this is obviously a huge problem. But my point in this is that if we want, why did we want to have intrusion detection system in the first place? We wanted a complementary system, a system that can detect when other systems fail. When will probably our security systems fail? When an unknown vulnerability or a custom vulnerability is used against us. So, when are misuse detectors useless? Exactly in the moment where we need them most. So, it is my opinion that, well, I wouldn't say that money slated on intrusion detection systems will be better spent on firewalls. But surely, misuse-based systems are not the solution, or are not a complete solution to our problems. So why are we stuck with misuse detection? Why don't we use anomaly detection all the day? Trouble is, doing anomaly detection is difficult. I've been studying how to do anomaly detection for the whole of my doctoral studies. And I've read tons of paper about how to do anomaly detection. It's a very hard problem, because if you just think about it for a moment, if I give you the task of describing the normal behavior of a computer system, how do you do that? Which variables do you take into account? Which features, we call them features, do you analyze? CPU activity, network activity, distribution of different types of protocols on the network, inbound to outbound rates of packets. There's an infinity of features and variables that you can measure on a system. And the more complex the system is, the more difficult these variables are to get in the first place, to measure. And in the second place, once you have these variables, how do you fit them? There's a lot of papers and there's a lot of products even that are based on the idea of, well, I do some statistics on that. Yes, but what? I just look to the average and to the standard deviation and blah, blah, blah. and I just look to this data and I put it on a neural network, a genetic algorithm, whatever, and look, it detects some attacks. More on this point later. But in general, you can understand that it's difficult to describe the normal behavior of one of these variables. Also, misuse detection systems usually do not generate a huge load of false positives. If you have false positives on a misuse detection system, you have written a wrong rule. On the other hand, anomaly detectors generate by their nature false positives. So if you want to go down the anomaly detection path, you know you will accept a huge load of false positives. And sometimes they are not even false positives. Because if I design an anomaly detector to work on the network, and suddenly, one day, a person in my office shows his colleague a new game, a new multiplayer game, and everyone begins to play this multiplayer game, and this multiplayer game uses some kind of wired protocol my system has never seen before. By the end of the day, my system will be blinking and shouting that there's some anomaly going on. Is it wrong? No, it isn't. It's anomalous. It's different than what it has seen before. Is this an attack? Usually not. So you have to deal with false positives, and you have to reduce them. Usually you reduce them through the careful setting of thresholds. But there's a basic problem of anomaly detection. It is that if you choose the wrong variables or the wrong model for these variables, your system will be blind. Just think of a detector which detects oscillation in bandwidth, most simple form of anomaly detection on a network. If I make it sample my network at 5-minute intervals, which is admittedly stupid, but it's an example, and the oscillation takes place in the middle of one of these intervals, then it will be canceled out by the rest of time. So if I only look at averages, I will never see anything. This is true in a more complex way. If you choose the wrong variables or the wrong models to fit the variables, even if the variables are correct, a wrong model will make your system blind. Trouble is how to design this model. And this is what I do. On top of all of that, there's an issue which, in my opinion, is difficult to get around. An anomaly detection system will tell you that there's something wrong. No more, no less. What's wrong is your guess. If you're lucky, and if your system is particularly well built, it will also tell you how it detected something anomalous. For example, it will tell you, look, this variable is anomalous. So you can have some hints for figuring out what's going on. But in most cases, you will never get an alert which is as precise as the alert of a misuse detector. Misuse detector says to you, this particular vulnerability has been used on this particular host, and guess what? Your host was vulnerable, and guess what? The attacker got back a shell. That's way better if you want to do reaction. So, anomaly detection systems, until now, are not very useful for intrusion prevention. In my lab, we study anomaly detectors based on unsupervised learning. Unsupervised learning is a nice term. What is a learning algorithm? It's a very simple thing. It's any type of algorithm that can improve its performance while you use it. The more you use it, the more you train it, the better it gets at performing its tasks. Learning algorithms are divided into two different sets. Supervised ones are the ones where you train the algorithm by giving it examples of inputs and outputs. For example, the basic multi-layer perceptron, the neural network that you have studied if you have studied anything in neural networks, it's the simplest form of neural network, is supervised learning algorithm. You show it samples of inputs and results, input and result, input and result, then you give it an input and you make it calculate the result. On the other hand, there are unsupervised algorithms that can learn on unlabeled data. They can learn on data which has not been tagged. And they are very curious because one of the things these unsupervised algorithms are very good at is detecting irregularities in data and flagging whatever behaves irregularly. Remember something? An unsupervised learning algorithm is very, very similar to the basic definition of intrusion detectors. I've already presented here in this hotel my network-based intrusion detection system. Today I will talk about host-based intrusion detection. What's the state of the art? Host-based, anomaly-based intrusion detection, lots of research on it, gazillion of papers, everyone has written one. Every single student of a computer security course has written an intrusion detection system using whatever algorithm he had at hand. So, let's focus, because otherwise we will get lost. I don't have the time to explore everything. One observed feature, the sequence of system calls a process makes. Great feature. Tells you everything you want to know. What files does your process access? What does it do with them? It tells you everything. The sequence of system calls called by a process through its life is very indicative of what the process does. In fact, those of you who routinely debug programs may have used strace or something like that to understand what the heck is going on in a program. There's a lot of studies on this feature, on sequence of system calls. The base idea is that for each program, I can somehow characterize the sequence of system calls it normally performs so that I can detect deviation and flag them as anomalies. There's a lot of earlier studies, and they used basically everything. Markovian algorithms, wavelet transforms, neural networks, finite state automata, n-grams, whatever they had at hand, just on the sequence of calls. Of all these models, the most interesting one is the Markovian model, because, in fact, it comprises most of the others. Neural networks are a case apart, and n-grams are a case apart, because they would be comprised by Markovian models, but only by a particular type of Markovian models. But the interesting turning point is asking ourselves, well, but is the sequence of system calls really so interesting? It is. If someone gets to execute its shellcode in the context of your process, probably its shellcode does not match the sequence of system calls that you normally make. But on the other hand, what usually doesn't match between the action of an attacker and the action of the real program may not be expressed by the sequence as much as by the arguments of the calls. And so why didn't anybody think of characterizing the arguments of the system calls? Because it's difficult. It's complex to handle arguments that are different. They're heterogeneous. It's difficult to handle them automatically. The only attempt was work done by Giovanni Vigna and others called syscall anomaly or libanomaly, libanomaly.org. But let me step back for a single moment. One of the basic tasks for unsupervised learning algorithms is time series learning. What's a time series? A time series is a sequence of observation over time. For instance, you observe the temperature of Las Vegas over a year. 40 degrees Celsius, 42 degrees Celsius, 41 degrees Celsius, and so on. Once a day, once every 2 hours. You will have a data which is a time series. So, if a syscall is an observation, a time series of syscalls is a program. A program is a sequence of syscalls. So, if this time series of syscalls is really a good description of the behavior of the systems, and how could it not be? It is a good description. Attacks should be probably turn out to be outliers. What's an outlier? An outlier is an observation in a time series which is so different from the others that you begin to wonder that maybe you were drunk when you did the measurement, or something else funny happened. An outlier is something that is totally wrong in the context. So, what's the problem? We have time series of system calls. We analyze the time series of system calls. We find out outliers. Anomaly detection done. Problem solved. Where's the problem in this? First problem. Traditional definitions for finding out outliers in time series are based on a simple assumption that the time series is made of a sequence of continuous values. So, values that are real numbers. System calls are not real numbers. They are what we would call qualitative or categorical values. Open is different from another system call, from a read, from whatever. But really, you can map those system calls to numbers, but these numbers do not have a real meaning. If you map open to 1 and set UID to 2, this does not mean anything on the fact that these two system calls are close. So, all these definitions based on the distance between numbers cannot be applied. The only approach which gives us a way to define time series outlier detection for categorical values is Markovian models. What's a Markov chain? A Markov chain is basically, well, there's the definition over there, but I don't really want to lose everybody of you. So let me just sum up in this way. A Markov chain is a stochastic process, which means a process which has random results. It does not go always the same way. Where there are a finite number of states, well, this sounds good. System calls are finite. There's a stationary probability of transition from one state to the other, so it doesn't change over time. During time, you move on the model, but the model itself does not modify. And it has the Markovian property, which means that what happens in the next step depends only on the k most recent steps. And usually, we call a Markov chain a Markov model of order 1. So a Markov model where you take into account only what has happened in the step before. A first-order chain has transition probabilities which can be expressed on a very small matrix with S rows and S columns. Probability from A to B, from A to C, from C to A, from C to B, etc. It's a square matrix with S rows and columns. If you add in the nth order property, which means that you keep track of the n most recent states, you need S to the nth by S to the nth rows and columns, which means that each step you add into the description complicates the model in an exponential manner. So, for these reasons, most of the studies, and my own study as well, use first-order Markov chain models. They comprise other models. Finite state atoms can be simplified as Markov chain. N-grams are actually nth-order Markov chains. So you have probably already seen how a Markov chain is done. It's a bunch of states, probability of transition from a state to the other, and you can calculate very easily the probability of a sequence of states into a chain. It's very simple. You pick up all the states you traverse, you multiply the probabilities, and you obtain the conditional probability of the sequence. Well, the reverse problem is slightly more complex. Given a set of sequences, how do I train, how do I create the Markov chain which fits best this set of sequences? Well, usually, you will do this with a maximum likelihood model. Basically, you would create the Markov chain in which the observed sequences have the maximum probability. So if I've seen A, B, C, and then I've seen A, B, C, D, and then I've seen A, B, C, D, E, and something else, I train the Markov model by choosing the parameters that make this bunch of sequences as likely as possible. This can be done simply or through a Bayesian calculation. The simple calculation is what you will do normally for training Markovian models. What can be discovered in a very brief time if you try to experiment with this is that if you have null probabilities, so if you have transitions that have never been observed, they will be transitions without an arc in your resulting Markov model. This can be deleterious for your anomaly detection system because if you have a training set which does not show a particular transition, and then in some point this transition shows up, you will have a zero probability sequence, and so an immediate flag of anomaly, while it may be a normal condition for some reason. So there's another problem, which is the fact that if you pick up one of these sequences and you just try to compute the probability for a short sequence and then for a long sequence, obviously the probability for the long sequence will be lower than the probability for the short sequence because you traverse more than one arc which has a weight which is lower than 1. So every time you add a letter, every time you add a state to the sequence, you will invariably lower the probability. There are some mathematical tricks here to smooth this probability. I wrote a paper which has been published in a congress in Turkey, which is called Behavioral Intrusion Detection. If you look it up on the internet or on my webpage, you will find it, and it has all the mathematics you may want to explain this trick. But basically, what happens is that you need a Bayesian calculation to compute the probabilities, and as maybe you already know, in Bayesian calculation, there's a well-known problem, which is the problem of determining the so-called prior probability. And in that paper, I find out a prior probability for such a model. Well, you may have heard talking of hidden Markov models. What's a hidden Markov model? It's a Markov model where we do not really see the states. So I don't see the ACGT state in the previous example, but I see something which is generated from the state, so a function of the states. It's hidden because I don't see directly the state, I see the function of the state. This adds up complexity in order to find out how likely is a sequence in a given HMM. There's an algorithm which is called the forward algorithm, which can be used. And when you try to determine which is the most probable path that can have generated a sequence, this is a mathematically complex problem which has been solved by an Italian named Viterbi, and the Viterbi algorithm is very well known. It's used in your regular GSM cell phones, for example. And there's another algorithm, which is the one we could be interested in. It's how to learn the parameters of an hidden Markov model from the sequences. And I won't go into the detail, but it's sufficient to know that there's an algorithm called forward-backward or Bohm-Welch, which can compute this for you. So if you decide that you want to model your system calls with hidden Markov models, that's not a problem. You can, it's a bit more difficult than using your regular Markov models, but you can do that. Actually, from my experience and my opinion, it's not really necessary in the case of system calls, but results might vary. So I was talking before of syscall anomaly. What's syscall anomaly? It's a model proposed by Giovanni Vigna, where each system call is evaluated on 4 models. On each system call, on each parameter of the system call, a string length is computed, character distribution is computed, structure of the string is computed, and the parameter is evaluated to see if it's a token. These models are theoretically interesting, very interesting, but they are flawed. In real world, they do not work. So what we did was to analyze them. For instance, the structural inference model, which tries to characterize the structure of a string, is fundamentally a Markovian model without probabilities. What happens is that since they did not take into account the 0 probability problem, if you If in your parameter appears a character that has never been there before, this is sufficient to make this particular model scream there's an anomaly. So since the syscall anomaly stuff automatically tries to understand if a model gives good results or bad results during training, what happens is that this model gets automatically tuned out because it generates too many false positives. So it's there, it's implemented, it's executed, but its results are discarded by the algorithm itself. The token search, again, you must predefine what is a token, so much for unsupervised learning. And again, you don't have probabilities. So if you have a token, which is, for example, a UID-GID combination, and there's a combination of UID and GIDs which you have never seen once, or you have seen, then it will be flagged as anomaly. But if you have a UID-GID combination that you've seen just once, while another UID-GID combination is seen 99% of the time, the seen once combination is not flagged as more anomalous than the other, which is not correct. So we evolved these models. We picked up the structural inference model and threw it away. As soon as we threw it away, false positives of the system halved, which is quite interesting. We implemented a model for file system paths because it's a file system is the most common parameter for which can be a string in a system call, and therefore it makes sense to have a model for this. We looked at structural similarities, so elements in common, /user /lib is more similar to /lib than to /opt/bin, for example, and the depth at which various elements are. We introduced a probabilistic model for token search, and we specialized it for UID and GID, because if you think about it, when you see a UID-GID combination, what you're really interested in is it 0? Is it between 0 and 1,000? Or is it above 1,000? Because these are the three classes of UIDs and GIDs, for example, on Linux systems. What we added two things, basically. The first thing was to correlate the various arguments of a system call. What did we discover? For example, we discovered that the open syscall is being used for thousands of different reasons, in thousands of different ways. So it does not make sense to create a model, one model, for the open syscall. The open syscall will do whatever it wants. We create sub-models. We create models for subtypes of open system calls. And this gives us the possibility to create more stringent models which fit better and which are easier to deal with for flagging anomalies. And to do this, we used a hierarchical clustering algorithm. Basically, we merged similar uses of open until we, merging subsequent uses, created more damage than it solved. And this generated a very useful distinction among different ways to use the same syscall, which we used also in the step of correlation. We added a correlation of the sequence of the system calls, because Giovanni was interested in studying, and he gave the first root study of how to evaluate parameters. But he didn't add in a time correlation. We did. And we correlated over time not looking just at the open or whatever else system call, but we correlated over time looking at the submodel of the system call. And this gave us much better precision and much better results. So what's clustering? Clustering means grouping things together so that similar things are together and dissimilar things are not together. Looks like a very simple thing to do. For humans, it's very simple. For computers, it isn't. We used a hierarchical agglomerative algorithm, which means that it's an algorithm that picks up the objects, finds out the two objects that are most similar, merges them, then goes again and again until merging means merging two very different things. There's a stop criterion. At that point, the algorithm stops, and you have clusters of similar things merged together and dissimilar things not merged together. So what's similarity? It's difficult to define. We had to fight to define, for example, similarity among paths, because it's difficult to say if /user, /local, /lib is more similar to /user, /lib or to /user, /local, /doc. Try to figure it out for yourself. It's not easy to express the reason why your brain tells to you, experienced Unix administrator, that /user, /local, /lib is similar in function to /user, /lib. Anyway, our clustering process aggregates similar uses of system calls. Let's take a simple example. FD format, very simple program, does very simple thing. These are the first few uses of the open syscall in FD format. What happens is that if you run a clustering algorithm, first thing that happens, the first bunch of calls is clustered together. Because if you see it, they have the same path, they have very similar names, and moreover, they have the same opening modes. Here they are expressed in a very curious way, but it's the way we like to read the output of the algorithm. Then, if you run again the merging algorithm, these two calls are merged together because they are similar. /devices, /pseudo, it's similar. Notice that at the third step of the merging algorithm, this one, which is slightly different from the former ones, gets clustered together with the library's opening. And at the end of the run, we have that. We have three clusters, one cluster with the opening of devices, one cluster with the opening of libraries, and one cluster with just one opening, which is the opening of a terminal character file. This is interesting because it creates submodels for different uses of open. So now we don't have open anymore. We have open1, which is the open which opens libraries, and as models tuned to the opening of libraries. We have open2, which is the open which opens devices, and as models that are tuned to the opening of devices. So if at some point in the open that usually opens a device, I will see an open of a file which does not mean anything in that context, I have much better possibilities of detecting it by using a subcluster of open than by using everything else. So we added a Markovian model. This is not very interesting per se because it's already been done. The model can be, it's a simple first order model can be trained easily with very few runs on regular programs. What happens is that some researchers suggest that one of the ways to create an anomaly detector is to statically analyze program paths. So you pick up the program code, you statically analyze which system calls can be called in which order, and you build the graph. This is wrong for two reasons. First reason is, if there's an error in that, you will just bring it over to your anomaly detection scheme. Second reason is that this does not generate to you probabilities of executing a particular path of the program. Because one of the things we are interested in is that some users or some systems may use just a subset of the capabilities of some programs. So I may be interested in the fact that a program is executing a path which has never executed before. So at runtime, our model gives out three different outlier indications. First outlier indication is how likely is the sequence so far. So I'm executing PS, I run it, I see the various system calls that are generated. For each system call, I execute the analysis of the arguments. I classify it as one of the types. I see the point in which I am in the graph, and I calculate the probability of the sequence up to this point. So this tells me how likely is the execution of the program until now. Second point, how likely is that this particular system call follows the particular system call that was here before? So how likely is the last step? This is a punctual indicator of when a programs get diverted. Third indication, how similar is this system call to other system calls of the same type? So I have a couple of punctual indicators of anomaly which should help me detect the attack in the moment when it happens, and at least one global indicator of anomaly, which even if I don't understand the exact point where my program gets diverted, after a while that my program has been diverted and is behaving in some other way, it gives me an alert that it's not executing in the same way it used to. So, at this point of presentation, many colleagues will give you the results and will tell you, well, my system detects 99% of attacks on the blah, blah, blah data set, and with a false positive rate of 5.2%. I like Dilbert. I think that Dilbert explains many things in information technology, and that strip of Dilbert is particularly enlightening. Dilbert, do you have the benchmark results? Do you want the 10-minute explanation of why this data is useless, or a simple, here you go? Amin says, here you go. I have presented at BlackHat Federal, and you can retrieve it on BlackHat website, all the reasons why most of the evaluation of intrusion detection systems, up to and including the DARPA intrusion detection system evaluation dataset, are useless, or mostly useless if you want to quote the Galactic Guide. I won't claim with you the false positive rates or false negative rates of this system on the DARPA dataset. We evaluated it on the DARPA dataset, of course. Everyone does that. The problem is, if you pick up the host-based data of the DARPA dataset, which is a set of BSM Solaris audit files, I can bet with you that I can write a Perl script or a bash script or a Python script that detects all of the attacks with 100% accuracy and 0% false positive rate. Why is that? Because every single one of those attacks is a buffer overflow. And every single one of those attacks begins with a very long string being used in a system call. So if you just detect all the strings longer than 300 bytes in system calls into that data set, you will find every single attack with a 0% false positive rate. That data set is useless. If you see each single anomaly detection, misuse detection, IDS paper in the world uses that data set. So it's not like I don't have the results. I do. If you go and look up my doctoral thesis, you will find the results on the DARPA data set. But it's useless for me to show them up to you, because in the real world, everything will be different, right? So what can I say instead, qualitatively? I can say that my system can contextualize deviations. So whenever you find out that a program has deviated, you have a very good guidance that tells you exactly in which point the anomalous execution began. Second important result is that using the clustering of system calls grants a much better granularity and makes it so that the system on real-world examples behaves so much better than competitor systems, which are instead based on just the type of system call. Why is that? That's because the DARPA evaluation dataset is 1999 or 1998. It's been an age. They use mostly interactive software programs run on the common shell, not daemons, not servers. So what happens is that in a program which executes on the common shell, it's not really important if you have an open of one type or open of another type, if the buffer overflows is always present in the first parameter of the open system call. So I concluded my talk. I tried to argue with you that intrusion detection systems are needed, that current intrusion detection systems suck, that anomaly detection systems are needed in order to have some useful detection schemes. I tried also to show you some of my research in how to make a better unsupervised learning anomaly detection system based on system call sequences. Currently, this system is not running online, still running offline on batches of logs of evaluation. There's no reason it couldn't run online. Actually, we are integrating it to run online. There's no reason, in fact, that this could not be integrated in an intrusion prevention system of sort. If it behaves as well as I hope it will, it could be integrated, for example, with an intrusion prevention system. Core Force is the one that is ringing in my mind right now, but you may have better suggestions. What we need really, but this is a need that it's not just my need, but it's a need of our research community, is that someone, somewhere, comes up with a good idea on how to test intrusion detection systems. because until we must rely on 1999 and 1998 data sets, admittedly wrong, deliberately simple, which have nothing to do with the reality of today, well, I am convinced that we will not get much further in our research. We need a consistent baseline, a consistent standard for testing intrusion detection systems. Because if we don't know how to say if an intrusion detection system is better than another, how are we going to say if our new idea for an intrusion detection system is better than the idea we had yesterday? So thank you very much for your attention. You have been very patient to bear with me. I'm not at peak of my well-being today. I'm jet lagged and feeling a bit ill. But thank you very much for bearing with me. And if you've got any question, I'm here to answer you. Thanks. Thank you. Yes, please. Yeah, that's one of the big issues. I cannot really answer that question because currently it's implemented in Perl, so performance is very much not of note. Usually, Markovian type algorithms are just multiplications at runtime, so it's very fast. Training is a bit complex because there's all the clustering type and so on, but the decision at runtime, which is what really matters in terms of performance, can be performed quite quickly. Yes, please. Mm-hmm. It will fly below this radar. It will fly below this radar. If, I repeat the question, if someone writes shellcode that does not actually execute a system call, this was the question. Of course, since I'm just tracking system calls, that will be below the level I'm looking at. It's exactly the discussion I was making, the point I was making before. If you have an attack which shows up in variables you are not looking for, you don't see it. Yes?
What is the amount of data that we need to characterize the system, not only with the traces of it, but in positive parameters? What is the smallest string that you can use, or the smallest number of sequences?
The question is about the dimension of the training data. Actually, obviously, you can't really characterize very short sequences of system calls, because if they are very short, either they are fixed, and then you will have just a 1 probability, or you will just end up with a very confused Markovian model, which does not tell you very much. Regarding the number of execution instances of the programs, that's one of the issues actually with current training sets for IDS evaluation. They have too few executions. For example, for some programs in the DARPA evaluation data set, there's like 20 executions. 20 runs are not enough. Another problem is that if you want to automatically generate data for this type of evaluation, so if I'm just a researcher, I don't have a network, so I don't test it on a real-life network, I need to generate automatically data. If my scripts generating the data, the scripts that emulate the interaction of users are too simple, I will always follow some fixed path of system calls. So in a real-life situation, this will not be true. And this is an issue which is currently very present in the literature of my research area. If you look at the literature of IDS research, I would like you to pay attention to how the traces were generated for various evaluations, because that's pretty much the point of the problem. Well, thank you again for your attention.